Today we're going to start our new unit. We're past the hump now. We're on our second to last unit, third unit out of 4. It's called uniform circular motion. We've talked about uniform motion before, motion that exhibits a constant speed. We've talked about uniform accelerated motion, motion that exhibits acceleration but a constant acceleration. Uniform means kind of constant. So we're talking about circular motion. We're talking about an object going in a circle. Specifically, uniform circular motion is an object going in a circle at a constant speed. Does that make sense? Now, of course, it's entirely possible to get a situation where an object is going around in a circle and speeding up or slowing down at the same time. I know when I take that on-ramp to Highway 2 from Okotoks, you guys know what I'm talking about, right? The one that goes almost a full circle around. I slow down as I go onto that on-ramp. And then as I get close to the end, where you got to go up that hill and merge into traffic, I speed up while I'm still in the circle. That's not uniform circular motion. Because although I'm going in a circle, my speed is changing. Uniform circular motion is when you're going in a circle and the speed is constant. Does that make sense? Okay? Circular motion with a constant speed. Now, we're going to define a few new terms here. A few new terms that relate to both this unit, circular motion, and next unit that we're going to do on simple harmonic motion and waves. First one is frequency. You've heard that word before, right? In what context have you heard the word frequency? How frequently have you heard the word frequency? How many times in the last year have you heard the word frequency?
Heard it about radios before.
Sorry?
About radios.
Okay, about radios, yeah. If you tune your radio to, so last night I came home from the hockey game and I tuned it to 960 so that I can listen to the post-game hockey game stuff, right? It says 960 kHz. The frequency of the waves, the radio waves, is 960 kilohertz, or 960,000 cycles of a wave per second. So what does frequency mean then? If we're talking about a frequency of 960,000 cycles per second, I asked the question, I said, how many times in the last year have you heard the word frequency? The frequency is a number of events that take place in a certain amount of time. In the context of circular motion, we would say it would be the number of revolutions in a certain amount of time. Specifically, the number of revolutions per second. Does that make sense? So, something's spinning around. How many times does it spin around per second? It may be 50 times per second. In 1 second, it may be 0.3 cycles per second, or 0.3 revolutions in 1 second. So in other words, it may take 3 seconds in order to go around once. Okay? Frequency, we're going to say, is the number of cycles, we'll say, because that's the general definition. But specifically in the context of circular motion, it would be revolutions or rotations. You guys know what the difference between a revolution and a rotation is? The Earth revolves around the sun. It moves around the sun. The Earth rotates on its axis. Make sense? So rotation kind of infers a spinning. Revolution infers motion around something. But it's still both circular motion. So the frequency is the number of revolutions or rotations, or in general, we say the number of cycles per unit time. And that unit time that we usually use is a second. Now, you could say, like I asked a few minutes ago, right, how many times have you heard the word frequency in the last year? Number of events per unit time, number of events per year. You can use year as your unit of time, but usually it's going to be seconds. How many times have you heard the word in the last second, right? How many times per second have you heard the word? Okay? How many times per second has the DVD spun around, rotated on its axis? Okay? How many times per second has the merry-go-round spun around? The units for frequency would be, we say cycles per second or rotations per second, or sometimes we just say 1 per second, 1 over seconds. Or the unit that means the same thing as 1 over second is an Hz, hertz. Luke, when he gave me the example, the good example a couple minutes ago of where he's heard the word frequency before, said in the context of a radio. When you look at a radio, AM, it'll say 960 kHz, kilohertz, 960,000 cycles per second. If you look at FM radio, what radio station do you guys listen to if you listen to anything? I know for the most part you listen to Spotify or something, but what, if you listen to a radio station, what would you listen to? Okay, so the Eagle 100.9. Okay, that's FM radio, which is megahertz, 100.9 megahertz, or 100.9 million cycles per second. So AM radio is thousands of cycles per second. FM radio is megahertz and millions of cycles per second. A hertz is 1 cycle per second. A megahertz is 1 million cycles per second. All right, so it's the number of cycles per unit time, usually in seconds, and we can express that definition as an equation. We could say F is equal to the number of cycles over the time. Can you guys read that? Maybe not. Let's try to make that a little bit neater. Now, that equation, we'll call it an equation, I guess, but it's not really an equation. It's really just a definition, right? It comes back to the definition of frequency, the number of cycles per unit time. Okay, it's number of cycles over the time. It doesn't appear on your data sheet. It's because it's a definition. Okay, period. In the context of circular motion or wave motion, we would say the period that's actually the opposite of frequency, the inverse of the frequency. As opposed to saying it's the number of cycles per unit time, we would say it's the time per cycle, or time per revolution. How much time does it take the Earth to go around the sun once? 365 days. So the period of the Earth is 365 days. How much time does it take the Earth to rotate on its axis once? 24 hours. So the period of the Earth's rotation, the time for one cycle, is 24 hours. How much time does it take the moon to go around the Earth? Okay, 28 days. So the period of the Earth's revolution around the moon's revolution around the Earth is 28 days. Okay? The time per cycle, of course, the units for that would be typically at least seconds, although we can use days or hours, like we did when the Earth was going around the sun or when the Earth was rotating on its axis. The equation, well, not really the equation, but the thing that's like an equation that represents the definition. If frequency is the number of cycles per unit time, then we would say the period, which is, by the way, is a capital T, not a lowercase. It's a time, so it's a T, but any time is a lowercase t. Specifically, the time for one cycle or the time for one revolution or one rotation is a big T, capital T, the period. It is not number of cycles per time, but rather the time over the number of cycles or number of revolutions or rotations. In other words, we could say, look, if you look at this equation here that we have for frequency and the equation we have for period, in other words, we could say T is equal to 1 over the frequency. Notice how they're opposite like this? Notice how they're inverse? Cycles per time, time per cycle. So they're completely inverse of one another. That means the period is 1 over the frequency. That red one, by the way, period is equal to 1 over frequency, does appear on your data sheet. The green ones don't, the red one does. And finally, speed. Of course, we know what speed is, right? How fast something's moving. But in the context of uniform circular motion, we can derive a new equation for it. Look, we know that speed is represented by the equation v equals d over t. And we can use that here again because we're talking about uniform circular motion, right? Object going at a constant speed around a circle. That's a group A problem, really, right? Constant speed. V equals d over t. What's the distance around a circle once? What's the distance around a circle? What's that called, JC? Yeah, it's the circumference. Do you guys know an equation for the circumference of a circle? I don't know when you learned that. Like, it's probably been a while, like grade 7 or something, grade 6. Anybody remember? Yeah? Diameter times pi. Sometimes people call it 2 times pi times the radius, right? The diameter is just twice the radius, right? So it's exactly the same thing. I like to call it 2 pi r. I'm not sure why, but that's what I usually call it, and that's the way I'm going to write it because that's the way that it's going to be on your data sheet. So what I'm going to do here is I'm going to replace the distance around the circle with 2 pi r, the circumference of the circle. Okay, if we're using the distance around the circle once, the circumference, then we need to know the time around the circle once. What's the time around the circle once? The time for one revolution or rotation. What do we call that? JC told me the distance around the circle once was the circumference. The time around the circle once is the? Okay, this is what ties it together. This is what puts it together. It's staring in the face. No, that's not the time around the circle once, but you're close. What is it? Well, it's seconds, yeah. The time for one trip around a circle is the period, yeah. So we're going to say, if we're writing 2 pi r, the circumference for the distance around the circle once, then let's write period t for the time around the circle once. That equation also appears on your data sheet. So whatever you see in green there is, well, I guess the v equals d over t appears on your data sheet as well, although somewhere else. Whatever you see in green is more definition. Whatever you see in red are equations that appear on our data sheet. What units do you think r would be, the radius of the circle? Do you guys know what radius of the circle is, by the way? If here's the circle, this would be the radius, right? This is from the center of the circle to the outside. Christine said the circumference is pi times the diameter. Well, because the diameter is from one side to the other, right? So 2 times the radius would be the diameter. This is the way we write it, but if you use pi times diameter, that would be okay as well. It's just that we don't write it that way. Okay, here's a nice little question to internalize what we just saw here. It says the hard drive, it says in figure 5.16, we don't need a picture of this. The hard drive in a computer, it spins. You guys know that when you store data in your computer now, now we often store it in a cloud, right? A hard drive somewhere in probably China, I don't know. But when you store it locally on your computer, it's typically stored on a hard drive. Sometimes it's on a solid state drive. You see a computer advertised with an SSD. That's a lot quicker and a lot more efficient access of data. So it ends up being a faster computer as a result of an SSD. But SSDs are more expensive. Okay? And it's harder to get a big SSD than it is to get a big hard drive. A hard drive, we still see them a lot on computers, okay? Even though it's the same technology that was used when I was your age. Okay? A hard drive is based on this little thin platter that spins around and stores magnetic patterns. Okay? And that's what stores your data. And it spins around really, really quickly. In fact, it makes one complete It says revolution. That's actually the wrong word. If this platter spins around like this on its axis, it wouldn't be one revolution in this amount of time. Rather, it would be one rotation in that amount of time. It doesn't really matter. We know what they mean, right? In 0.00833 seconds. So we got like 8/1000ths of a second it takes this thing to spin around once. We want to know its frequency in hertz, which is the standard unit, but also in RPM. What does RPM stand for, you think? Yeah. Good, revolutions per minute. So revolutions or rotations per minute. Hertz is rotations or revolutions per second. RPM is rotations or revolutions per minute. Okay, what do we have given to us here? What is this number, 0.00833 seconds? I mean, clearly that's a time, right? Do we just write down little t? That's my time? Well, it is a time, but we know more about it than just general time. Specifically, we would say that is the, what's the word? The period. The time for one cycle. The time for one rotation. Or as they call it, a revolution. Whoops. Just did the same thing. I erased a little t and replaced it with a little t. We'll call it big T. Don't get that mixed up, okay? It's important when you're writing the period to write it as a big T. Because it's not just any time. It's a special time. Okay, it's a time for one, exactly one rotation or revolution. Okay, there's big T. That's all we got, isn't it? We're looking for the frequency. Any ideas? Any ideas here? Oh, come on. Check your data sheet. Or look at your notes. Want to find the period. Sorry, want to find the frequency. Got the period.
Could we divide 1 by 0.0?
That's exactly what we're going to do. We're going to say t is equal to 1 over f. That's the equation that appears on your data sheet, except we're going to solve for frequency. So we'll rearrange that. Take the f up by multiplying and the t down by dividing. Looks like this. F is equal to 1 over t. 1 over 0.00833 seconds. I'll show you a little trick on your calculator. It's not a big time saver, but sometimes it is, depending upon the context. If we type in 0.00833, and then we hit this little button here, x to the minus 1, that's the same thing as saying 1 over that. So we say it's 120.048. What's the units for that? Well, let's round it to 3 digits. We could say it's 120 1 over seconds, rotations per second, or we could say it's 120. It hurts me, guys, that nobody's coming up with the answer for this except JC. What is it, JC? Hertz, HZ. Exactly the same thing, right? So you can express it either way. In fact, you could even say, if you wanted to, 120 rotations per second, or RPS would even work. Hey, why did I write down the number up here, 120.048? Why didn't I just round it right off the top? Oh, sorry. Yeah, Jack? Yeah, don't round until you get to a final answer. Now, I have a final answer, but I also need the unrounded number to get to another final answer. Any idea how I'm going to convert 120 rotations per second into rotations per minute? Yep. Yeah, that's exactly what I'm going to do. Okay. Some of you are going to think like, well, I know it's 60, but is it multiply by 60 or divide by 60? Well, try dividing. 120 divided by 60 is 2. If I have it spin around 120 times in 1 second, is that going to be 2 times in 1 minute? That doesn't make sense, right? Of course you're going to have more rotations in a minute than you're going to have in a second. So it must be times by 60. So that's what we're going to do. We're going to say 120.048 times 60 gives me a frequency of 7202.88 RPM, rotations per minute, or we're going to round that to 3 digits, 7.20 times 10 to the 3 RPM. That's actually pretty standard, pretty typical for a hard drive speed. You can buy hard drives that spin faster. What would be the advantage of that? Well, your computer could access the data quicker, right? If it's spinning faster, then it's like saying, you get this conveyor belt. You get this would be kind of a neat idea for a store, actually. Instead of walking around the store, everything in the store is on a conveyor belt and it goes past you. You just get to sit in your chair and pick things off as it goes by. The faster it goes by, right, the quicker you can access the stuff, right? The faster that conveyor belt goes by. Well, the faster this thing spins, more rotations per minute, then the faster your computer can access data. Okay? The ideal is to have, as I said, that SSD, that solid state drive, where it's not spinning and you don't have to access it in the same way. Does that make sense? Yeah? Okay, has everybody got that copy down? Okay, let's take a look at those three questions, please, on page 250. All right, number 3 says a medical centrifuge is a device that separates blood into its parts. The centrifuge can spin it up to 6.0 times 10 to the 4 RPMs. What does RPM stand for again? Yeah, it would actually in this context be rotations per minute as opposed to revolutions per minute, but it doesn't really matter if you call it revolutions per minute. What's its frequency in hertz and what's its period? Just so you know, we see medical centrifuges, but we see centrifuges in other contexts as well. A centrifuge, the way it works is it spins, and then it uses the principle that heavier things have more inertia, and heavier things want to go to the outside of the circle more than lighter things. So, because of that. Now, I won't explain right now exactly why that happens right now, but we'll explain that tomorrow. But for now, like you spin something around, heavier things go to the outside. So what it does when you have a medical centrifuge is you put the blood in it, and this has to be a special test tube. Not a normal test tube will break, but a special test tube, and it separates the blood into its components. The heavier parts go to the outside. A few years ago, the big thing was Iran developing what's called enriched uranium to build nuclear bombs. And now you never hear about Iran doing it. Now it's all the talk about North Korea, right? But a few years ago it was all Iran. And the reason why the rest of the world didn't like what was going on is because in Iran was that Iran was using these centrifuges to produce what's called enriched uranium. Uranium occurs in, do you guys know what an isotope is? An isotope, like different versions of elements, different number of neutrons, elements. Well, if you take a big chunk of uranium, it's there's like something like 98% of it, of that uranium, is useless in building a nuclear bomb. But just a couple percent of it is useful in building a nuclear bomb. But you got to separate it, and it's hard to separate. It's chemically, there's nothing chemically that you can do to separate the good uranium from the bad uranium. So what you do is you put it in a centrifuge and you spin it really, really fast. And like it's not quite as simple as that, but the gist of it is you separate it using the centrifuge. The heavier parts of the uranium go to the outside so that you've separated the fissionable uranium, which is what you could use to produce a bomb, from the useless uranium. So that was the big deal. That was the big concern. We don't seem to be all that concerned about it anymore because now we got North Korea that we're worried about. Anyways, this is exactly the same principle, except you're using it for better purposes. You're just separating blood into components so that you can give somebody has an accident. They don't necessarily need, or a disease, they don't necessarily need a pint of blood. They need a certain amount of platelets or a certain amount of some component of blood here. All right, so anyways, this centrifuge can spin at speeds of up to 6.0 times 10 to the 4 RPMs. What does that mean? What variable is that? 6.0 times 10 to the 4 RPMs, rotations per minute. Frequency, period, something else, speed. Rotations per minute. Is that how long it takes for a rotation, or is that the number of rotations per unit time? It's what? It's the frequency, yeah. Now, it's not the frequency in the units that we want. Okay, we want the frequency in rotations per second, right? So let's do that. How are you going to get the frequency in rotations per second or in hertz? If it's 6 times 10 to the 4 times in a minute, then how many times is it in a second? Ethan, you know this because you did a question that was backwards to this before. What is it? Yeah, 6.0 times 10 to the 4 divided by 60. Gives me 1,000 rotations per second. So that's going to be 1,000. We'll say 1 over s, or we could just say 1,000 hertz. There's the first part done. What's its frequency in hertz? What's its period? Well, the period is simply going to be 1 over the frequency, which is 1 over 1,000, which is 1.0 times 10 to the negative 3 seconds. 1.0 times 10 to the negative 3 seconds. So it takes 1/1000th of a second for this thing to spin around once. Here's another one. The pebble is stuck in the treads of a tire at a distance of 36 centimeters from the axle. It takes 0.4 seconds for the wheel to make 1 revolution. Again, there really shouldn't be 1 revolution. It should be 1. Wheels don't make revolutions. Wheels aren't orbiting around something. Wheels are rotating. So really it should be a rotation, right? But whatever. What do we got here? What do you think this 36 centimeters is? Here's the axle of the tire. What variable is that? It's radius, not diameter, right? It's radius. The radius, I'm going to say, is 0.36 meters. What's that 0.40 seconds? It takes 0.4 seconds to make 1 rotation. That's the period. So we're going to say big T, not just T, big T is 0.4. And we're looking for the speed of the pebble. We're going to say V is equal to 2 pi r over big T. 2 times pi times r is 0.36 divided by big T. The period is 0.40. Let's figure out what that is. 2 times pi times 0.36 divided by 0.4 gives me 5.65. Is it 5.65? What should I round that to? That should be 5.7, right? I just noticed that this is 3 digits, but this is 2 digits, so we should round it to 5.7 meters per second. I don't have this on my bike anymore because now, you want to measure your speed when you're on your bike now, or the distance you traveled. You just use your phone or a watch. My watch has GPS on it now, for heaven's sake. I can know how fast I'm walking, let alone riding my bike. But it hasn't been that long that we've been able to do that. 10 years ago, we wouldn't have been able to do that. 10 years ago, I had a little, we called it a bike computer, but really all it is just this little $15 device on my handlebar that would tell me how fast I was going, and it would tell me how far that I'd traveled. It was really, really simple technology. You put this little magnet on a spoke. It didn't matter where you put it on the spoke of one of your tires, or on one of your wheels. And then you put another little thing that was connected to a wire on the fork, that goes down and holds the wheel on. You know what I'm talking about? So then as this little magnet, let's say right here, on this spoke right here, spun around past this little piece of metal, it would generate this little electric current every time it went by. Now, it didn't matter where you put it, because in the end, I had to program into that little bike computer, not where I put the little magnet. I could have put it here, I could have put it here, it didn't make any difference. I had to program the radius of the wheel. And then this little bike computer simply measured how long it took for this to make 1 complete rotation. Does that make sense? Now, it took the same amount of time to make a rotation here as it did here. Didn't make any difference. What mattered is the radius of the wheel, and the time that it took the wheel to go around 1 time. And then this little bike computer just did this calculation and then told me almost instantly, this is how fast you're moving, 5.7 meters per second, and this is how far you've traveled. Does that make sense? Yeah, I don't see those very often anymore because, unless you're a little kid, that's 8 years old and doesn't have a phone, you don't need that anymore, right? Okay, take a look at these questions on 251, please. Okay, let's have a look at number 2 here. It says, in 2006, an Alberta astronomer discovered the fastest spinning collapsed star, which is called a pulsar, ever found. It has a radius of only 16.1 kilometers. Now, that sounds big, right? But, you start thinking about that. That's the radius of a star. This is a star that has a radius of 16.1 kilometers. That would mean that this star, from one side to the other, in other words, the diameter of it, would be about here to not quite downtown Calgary. You can drive from one side of the star, well, assuming you could drive on the star. Okay, good luck with that. But if you could drive from one side of this star to the other in 20 minutes. 20 minutes, half an hour. It's spinning at a rate of 716 hertz, 716 times around per second. Yeah, good luck driving on that. We want to know what the speed of it is at the equator. All right, we know that the radius is 16.1 kilometers. We can convert that to meters. We can either say, just add 3 decimal places, or we can say 16.1 times 10 to the 3 meters, because a kilometer is times 10 to the 3 meters. So 16.1 times 10 to the 3, or 16,100 meters. What else we got? 716 hertz, what's that? Period or frequency? That's the frequency, and it's in the right unit, so we don't need to convert that. We want to find the speed. We know the speed is 2 pi r over the period, but we don't know the period, so we can find that by saying 1 over f. Right? T is equal to 1 over 716 hertz. So let's get that period. Remember the little trick that I showed you here? It's not much of a time savings, but 716 to the minus 1 gives me 0.001397 seconds, which we'll turn around and plug back into here. 2 times pi times 16.1 times 10 to the 3, divided by 0.001397 equals, let's say, 2 times pi times 16 times 10 to the 3, divided by, you get 7.20 times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay, that's pretty fast. All right, 7.20 times 10 to the 7 meters per second. Yeah? I think it's 7.24. Did we do something wrong? Oh, it's 16.1, isn't it? Not 16, it's 16.1. Okay. So that number is going to change a little bit, but the way we did it is correct. We just subbed a number in wrong. 7.24 times 10 to the 7. Okay, that's even faster. Not much, but it doesn't make much difference at that point. That thing is spinning around pretty quick. Make sense?